I want to give a leisurely presentation about measuring the universe. And I will sneak in a little bit of non-astronomy stuff at the end. I will talk about how mathematicians actually deal with infinity and how that is related to one of the most amazing insights of the last century. But I start with the astronomy stuff. Measure the universe. I mean, where do you start when you want to measure the universe? At home. Right? That's easy. You can put your ruler on the ground several times, and then you can measure distances. And then you know how far it is to the next train station or to your favorite water hole or wherever it may be. And I'm pretty sure that if you just stay at home doing nothing much else, you might be pretty much believe that, oh, the Earth might be just a plane, just flat. I mean, there is no real reason to doubt that after all. And so it should come as no surprise if you end up believing that the world is just a disk on the back of 4 elephants, on top of a gray turtle, great Artuin, which is just cruising through space, which, as those of you who might know some fantasy know, is known as a steady gate theory of cosmology. Yes, I am. Now, obviously, that is not what you are supposed to hear in an astronomy talk. You're supposed to hear something like that, the Earth is a sphere. But how do we know that? I mean, today it's easy, right? We have these nice photos from space, and it's pretty easy to see that it is a sphere, but someone had to figure it out to start with. And of course, it would be nice if I could tell you it was that person or that person. And yes, of course, there are contenders. And you probably heard the name of that contender here, Pythagoras, as in Pythagoras' theorem. There's something odd about that, though. If you go to the Wikipedia article on Pythagoras, what you will basically learn is that no one really knows what the guy really did. So he is real, yes, that's not doubted. But did he really prove his theorem? We don't know. What we know for certain is that he did not invent the theorem. I mean, that was well known before him. I mean, that goes back to Egypt, I think Babylon. So they knew these things. The main contribution to mathematics from the Greek probably was that they actually started proving things. They started asking the question, why? Can we actually show this? And that, of course, then is related in a way to astronomy, because when you start asking why questions, you start asking questions like, what does the Earth look like? Can we find out? How can we find out? So either Pythagoras or maybe another guy called Parmenides, we don't really know, came up with that idea that the Earth is not flat. The Earth is a sphere. Why? Well, they just had to look at the moon during lunar eclipses. Because one striking thing about lunar eclipses is that if you look at the shadow of the Earth, it's always round. It's always a nice circle. And as is illustrated in this image here, if the Earth was not a sphere but nice and flat, you wouldn't really expect a perfect sphere. You would expect something like elliptical or even stranger. So that's not the case. It doesn't seem to depend on where the sun is, where the Earth is. It's always a sphere. So that's one reason. And another reason, which might have been known to Pythagoras, because at least according to legend or history, he had been traveling quite a bit, is of course that if you travel north or south, you get to see different constellations. And that doesn't really make sense if you're on a flat Earth either. It makes real good sense if you're on a sphere. So whoever it was, someone in the 6th century before Christ came up with this notion the Earth is a sphere. And by 500 before Christ, everyone knew that. Every educated person was aware of that fact. And of course, there was sometimes that myth that people forgot that in the Middle Ages. Of course, they never did. I mean, that was a fact which was never forgotten. And of course, there are these legends that say Christopher Columbus was disbelieved because he said the Earth is a sphere. Not true, he was actually not really believed with his plans of going to India the way he wanted, not because of the Earth being flat or not flat, but because he completely underestimated the size of the Earth. And he was quite lucky that there was a continent in his way. So here's just a nice image of lunar eclipse where you can more or less see the Earth's shadow as well, nice and spherical. So I mentioned in passing the Earth, the size of the Earth. So now that we know that the Earth is a sphere, of course, the next question would be, actually, how big is it? And now you could start traveling and try to make all sorts of measurements, or you might just stay at home. That is sort of what this gentleman here did, Eratosthenes. He happened to be a librarian in Alexandria in Egypt. And he noticed in one of the publications that it was mentioned that, I think on solstice day, there was no shadow cast by a well in Cyrene. So the light was just shining into the well. So he did what librarians probably should do once in a while, stepped outside of the library and had a look at what does the shadow of a column look like in Alexandria. And he noticed that surely there is a shadow. And if you know the height of your column and the length of your shadow, you can obviously calculate the angle the parallel sunrise make with your column. And now, if you know the angle of the sunlight between your column, which is ordinate to the surface of the Earth, if you know that, and if you know then the distance between Alexandria and Cyrene, a little bit of geometry, then you can actually figure out what the circumference of the Earth is. So he did that. And according to what his units precisely were, which is not entirely known for 100%, he came up with a pretty accurate number of the Earth's circumference. Now, I personally am not sure whether that was more good luck or real accuracy. Because if you look at a map from that time, it doesn't look too accurate to me. So maybe I'm just unfair, but I wouldn't be surprised if that guy was not of lucky. But anyway, I don't think the important bit is that he was accurate or not accurate. I think the important bit is the idea that someone figured out how to do it. And that's pretty cool. So now we knew how big the Earth is, give or take a bit. Now that's nice. But then, of course, the next question is, can we do better? I mean, now that we know how big home is, we want to know how far away are the other things I can see in the sky. And of course, the first stop is the moon. I mean, how big is the moon? Is it just a tiny rock pretty close by, or is it really big and really far away? How would we know? And how far away is the sun to start with? How would I know? So basically at about the same time as Eratosthenes, so 3rd century before Christ, there was another Greek philosopher called Aristarchus of Samos. And he had two brilliant ideas. And the first brilliant idea is, what happens if you have half moon? Basically, if you have half moon, the sun, the moon, and Earth form a triangle with a right angle, as illustrated here on the screen. And that means that if I now can measure the angle between sun, Earth, and moon, I can basically easily calculate at least the ratio of the distance between moon and sun. Whether he actually really ever tried to measure that angle is doubtful, because it's really difficult to measure. He gave a value of 87 degrees, which is not really true, but the Greek at that time wouldn't have had the capacity to measure that angle precisely, because it's really, really close to 90 degrees. So, but either way, again, I think what really matters is there was that idea. And using this angle, he basically came up with the figure that the distance between moon, the ratio between the distance to the sun and to the moon should be somewhere between 18 and 20, which is only off by a factor of more than 10. But that's life. So now you might say that's nice, but it would be even better to know what the actual distances are, so that I can then also get the sizes. So how do I do that? Well, his clever second insight is illustrated here, and I have no idea how you would try to understand anything from this figure, from this manuscript, which is one of his books, by the way. This one is maybe a bit clearer, a bit more recent from Wikipedia. So the idea is you look at a lunar eclipse. Because obviously, when you have a lunar eclipse, you have a shadow of the Earth, you have a moon, and you can basically figure out what the ratio between the shadow of the Earth and the moon is by observing. And then there is one other insight you have, which is that if you look at them, the moon and the sun appear to have the same size in the sky. And just these two facts, together with the ratio you had for the distance between moon and sun, is actually sufficient if you just apply some geometry, some algebra, and correct all your mistakes you've made while doing the algebra, then you can actually figure out that I can actually determine the size of a moon, the length of the distance between Earth and moon and Earth and sun. I mean, that's pretty cool as well. So obviously the result Aristarchus got was completely off, given that his ratio between distance to the sun and distance to the moon was off by an order of magnitude already. But there is one thing which struck him nonetheless, which is the sun is really big, bigger than the Earth. So it's not just a ball of fire drawn in a wagon by horses and a god at the helm. It's bigger than that. And that led him, as it seems, to another idea, which is, hang on, if the sun is much bigger than the Earth, could it be that actually it's not the sun moving around the Earth? Is it maybe the other way around? Is the Earth actually moving around the sun? The only reason we know that he probably had this idea, is because there is basically almost only this one sentence in the book from Archimedes, where he basically states that Aristarchus came up with the idea that the sun is unmoved and the Earth moves around. Did he seriously believe in it? We don't know. Was the idea controversial? No. The ancient Greeks were quite happy with that idea, but it didn't really caught on well. I mean, obviously, the standard model of cosmology remained this one, the Ptolemaic worldview, that basically, broadly speaking, the Earth is in the center of the universe, and then basically everything else is moving around the Earth. And then somewhere we have the fixed stars, wherever that may be. And obviously the geocentric worldview has a bit of a bad reputation today. In a way, of course, that's understandable because it's not true. On the other hand, it's one of the most successful theories ever, in a way. I mean, that theory was basically valid for more than 1,000 years, which is pretty good for a theory. Why did people not believe in the heliocentric worldview? But pretty much because they didn't have to. Most of the observations were pretty compatible with the geocentric one. There were exceptions. I guess those are the things to sweep under the carpet and you don't talk much about it. And then there was that thing that stars don't move, it seemed. Stars are pretty static. And I mean, if we are moving around the sun, shouldn't the stars change over the year because we change around the sun? So our position relative to the stars changes? No. Shouldn't we feel the movement around the sun? So there were good reasons for the guys back then not to believe in the geocentric worldview. And one might point out that it was not a stupid model. Right? I mean, it was a bit more complicated than just saying that the Earth is at the center. Actually, the Earth is not in the center. It's slightly off from the center. And then, I mean, you've got the movement of the planets, which is made of, I think, the deferent, that's the big circle, and then the epicycle. And they actually are at constant speed, relative to that other point, the equant here. So it's not an easy model. So, and that is why, broadly speaking, managed to explain the observations pretty well. Now, for obvious reasons, that model is not particularly helpful if you want to find out more about the sizes in the universe. So for that, we had to wait basically for this gentleman here, Nicolaus Copernicus, who obviously then put forward the idea that actually the sun is at the center and then everything else moves around the sun. Not necessarily because it explained things better. I mean, Copernicus' model and the Ptolemaic model were pretty much equivalent when it came to explaining things. So, but there was this idea. And of course, other people started working with that idea. And the most notable person, perhaps for our story, is this guy here, Johannes Kepler, who spent years and years and years basically observing and trying to, or rather taking observation data from Tycho Brahe and trying to make sense of it. And he had a really hard time, because what he tried basically was to describe the circular motion of the planets around the sun. It didn't work. So in the end, he had the insight that maybe it's not circles. Maybe planets are actually moving in an ellipse around the sun. And so that then, of course, formed his first law, that a planet is moving around the sun in an ellipse with the sun at one of the two focal points of the ellipse. Then, as you might know, the second law is that the speed of a planet depends on the distance from the sun. And basically, you can phrase it by saying that if you have a line from the sun to the planet, as it sweeps over the plane, basically at the same time interval, it always means that the same area is swept. Which of course means that if a planet is close to the sun, it will be fast, and if it's far away, it will be slow. Enters, and that is where it becomes interesting to us again, his third law, which relates, well, basically the distance between a planet and the sun, or if you are really insist on it, the major semi-axis of the ellipse to the orbital period. And, well, there is the right side. That's basically just some constants and the mass of the sun and the mass of a planet. Now, planets have a convenient property that they are much smaller than the sun. So it's a good approximation to just ignore about the planet, or at least about its mass. And then you come up with this easier formula. And now on the right-hand side, you only have constants. So hooray, it doesn't matter what the planet is, how far away it is, this will always be the same equation. That's the good news. The bad news is that, unfortunately, there was still no way of really figuring out what this A is, this distance from the sun. Because what you could do is you could basically calculate ratios of distances, but not the actual distance. So what do we need? So now we need one length in the solar system, which we need to know for sure. And from there, we can do everything else. We can figure out how far away is the Earth from the sun and how far away are the planets and all that. How can we do that? One option which came up basically in the 17th century with astronomers, maybe we could use Venus. I mean, Venus, as you might know, has the habit of every once in a while crossing in front of a solar disk. Every once in a while, meaning that it does that basically in 1 year, then it does it again 8 years later, and then it takes a 105-year break, or even a 121-year break, and then there was another one, and then an 8-year gap, there was a second one, and then again there was that long break. So it's a rare event. But if you have such a transit of Venus, if you observe it from different locations on the Earth, obviously your point of view changes. And so Venus seems to move along different paths across the sun. And so astronomers had the idea that, hey, we can use that to measure the distance between Earth and Venus. And well, so, or rather the distance between Earth and Sun. I mean, you have it. So, but here was something new required. You really had to observe from all sorts of locations on the Earth. So it's not a one-man show. So probably for the first time ever, for the eclipse in 1761, the idea was born that maybe we have to team up. But that was a bit problematic in 1761 because there was a 7-year war going on between England and France and allies that hindered the process a bit. And that is nicely exemplified by one French guy, Le Gentil, who actually planned to observe that Venus transit. Unfortunately, by the time he arrived, or would have arrived at his destination, that destination had been taken over by the English. So disembarking there was out of question, so he had to move on. Unfortunately, moving on the ship back then was not particularly fast, and he ended up being in the middle of an ocean when the Venus transit happened. So he had to try and observe it on the ship. You can imagine that that was not successful. No, he was not too deterred, it seems, because, I mean, knowing that there would be another opportunity in 8 years' time, he decided, I might just stick around and wait and try again in 8 years' time. So he did that. In the meantime, the powers that be decided that you might as well have peace again. So in 1769, when that second Venus transit happened, there was no war between England and France anymore, probably helpful for international collaboration. And so now he planned to observe from Manila. Unfortunately, I mean, he set up early, he was basically there a year beforehand or something like that, and set up, was very happy. And but when he was told by the French Academy of Science, please observe it somewhere else. So he had to move, and he arrived in good time. He set up carefully. He had brilliant weather, basically weeks before, all the time. And then, of course, on the day of the Venus transit, it clouded up. Somewhat ironically, when he originally decided to observe it in Manila, the weather was fine. So he made his way back to France, only to encounter the next problem. He had been declared dead, but he had been away for something like, I think, 11 years. So his family had decided to basically take all his possessions. So he had to actually go to court to get his possessions back. He had some trouble getting his position back because he had been retired by the academy in the meantime, but he got that back as well. And I'm happy to report that he died peacefully in 1792. I mean, I guess that's real dedication to science back then. Other people were less lucky and they might have died along the journey. I mean, I guess illness was never far away on a ship back then. So they got a value, and the value they got, calculated in 1771 by the astronomer Jérôme Lalande, was 153 plus minus 1 million kilometers, which is reasonably close to the modern value. It was not as close and not as accurate as they would have liked to. And one of the problems they encountered is what is known as a black drop effect. There is actually a video here. So is it actually? Yes. The problem is, as Venus is approaching the rim of the disk, it is not a nice sphere anymore. Due to telescope effects and due to the fact that the brightness of the sun changes towards its edge. So nothing in life is perfect. That's very nice to see it. So wasn't perfect. Well, of course, there were then more Venus transits in the 19th century, and actually one guy who got involved with the Venus transits was none other than David Gill, who was actually the astronomer royal here at this observatory. And yeah, and he actually was instrumental in figuring out the precise value for the astronomical unit for basically the distance between Earth and Sun. But he did that not really with Venus transits, but he actually used the fact that we can get a parallax with Mars or asteroids as well. And so that turned out to be more precise and gave really good values. Now, of course, times have moved on since then, and values have become more accurate. I think at the moment, we know the distance between Earth and Sun with an accuracy of about 30 meters or something insane like that, which, given that the distance is about 150 million kilometers, is pretty good. Why do we know? Because today we have radar, right? And we can basically use radar echoes to measure the distance between, say, Earth and Venus very accurately. So the distance between Earth and Sun now is very well known. That raises the next question, of course, how far away are the stars actually? And obviously they must be very far away because they are not really moving, right? They are always in the same spot. Or at least they don't move in little circles or ellipses, so we don't see that. So how do you figure out? Well, you must again use that effect of parallax, of observing a star from different locations. And what's the biggest distance you can get on Earth? Well, you observe in winter and in summer from two different sides of the sun. So you get the full 300 million kilometer baseline. And then, of course, if you have sufficiently accurate instruments, you can see an ellipse. So who was the first one to have actually discovered such an ellipse for Alpha Centauri? It was Thomas Henderson, who happened to be the second astronomer royal here at this observatory. Now, he was a bit lucky, though. So shortly before he left Cape Town, he didn't stay long, I think less than 2 years, he received a letter from the astronomer from St. Helena, who pointed out that Alpha Centauri was moving. And so Henderson concluded that that probably means that Alpha Centauri is a nearby star, because why else would we see a proper motion? Now, so fortunately, he had observed Alpha Centauri carefully while he at the Cape. So when he was back home, he could now analyze this data. And yes, he found the ellipse. And now if this was a fairy tale, he would publish, got fame, and would always be recorded in history books as having been the first astronomer to have measured the distance to a star other than the sun. But as this is not a fairy tale, this is not what happened. So he did his analysis, he found the ellipse, and he didn't trust his data. And there had been attempts before, and they always had been turned out to be incorrect. So he decided that he did not want to be embarrassed, and so he decided not to publish. So 1 year later, 2 other astronomers, Bessel, I think in Germany, and Struve in Russia, made other observations, and they published, and so they got the fame of having been the first ones. But hey, the first observations which made it possible were actually done at this observatory. So now we know how far away stars are. The nearest one about 4 light years, which is, don't ask me what that is in meters, but is far, very far. Okay, that's great. And obviously you can do that with Alpha Centauri. You want to do that with more stars. And if you want to do that with many stars, you need a space probe these days, of course, such as Gaia here, which has, I think, measured the distance of 1 billion stars in the Milky Way, which I think is pretty insane. Now, to do that, basically it has to observe the same star over and over again. Why? Because if you actually look at the motion of a star as simulated here, you will actually see that it moves in these ellipses because of a parallax. But hey, it might also have a linear motion, or what astronomers call a proper motion, and that of course is superimposed. So you really have to observe it carefully because you want to know what is the linear motion and what then is the parallax, so that you can then use the parallax to actually establish the distance. And I think it did that with a millisecond accuracy or something like that, which I have no idea how they did that. One thing they had on board was a very accurate clock, because they really need to know when a certain star was visible. So I think that's really, really impressive. Now, one thing which is worth noting is that I have mentioned various names of various astronomers, and all of them were males, which of course is pretty bad, and of course just reflects the fact that gender equality was pretty much unheard of in those days. And even at the beginning of the 20th century, it was pretty much unheard of. Yes, women could do astronomy now, but basically they were relegated to doing the calculation stuff. So here you have it. This is a room full of computers. Yep, that's what they were called. So I'm not sure that is the server of them, but so these are the Harvard computers, highly skilled professionals. And I want to mention 2 of these computers, and that is on the left, Annie Jump Cannon, and on the right, Henrietta Swan-Leavitt, both of which play an important story in how to measure the universe. Why? Well, going back to Gaia for a moment, I mean, Gaia not only measured 1 billion distances, but also for considerably fewer stars, the actual spectrum. And so it actually could come up with this very modern version of what is known as the Hertzsprung-Russell diagram, basically plot the brightness of a star over the temperature of a star. And the important bit is that they're not scattered all over the place, right? So there is some reason to the diagram here. And the first step of using this diagram for trying to measure distances was, of course, to actually classify the stars properly. And that is where Anytime Cannon comes in, because she revised the classification scheme for stars. So different spectral classes, which correspond to different surface temperatures, so O, B, A, F, G, K. In case you wonder why is that order so strange, they got things wrong the first time around, and by the time they got things right, all these classifications were sufficiently entrenched so that they just kept the classification, but had to change the order. So be that as it may, what is a star? A star is basically a big ball of hydrogen. Maybe throw in a little bit of other gases and elements, but that's really it, a big ball of hydrogen. And so maybe it should come as no surprise that if you have two stars which have the same mass, they should be very similar, right? And that is this whole idea behind the main sequence here. If you look at that sequence, basically, there is a relationship between the temperature of a star and the brightness of a star. And if you do your astronomy, that also relates to the mass. And that's pretty cool. For most of the life of a star, basically, everything just depends on the mass of the star. And if you know the temperature of a star, you know how bright the star is, what the real luminosity is. And that's really cool. Why is it cool? Because that means that you can use main sequence stars as what is known as a standard candle. If I know how bright a candle really is, and I figure out how bright it appears to me, I know how far away it is. So, and that means that if I know how bright, say, a sun-like star is, I've measured that accurately for, I mean, I know the distances of nearby stars, so I can calibrate this, and then I just have to look at some other star, have to look at the spectrum, infer the temperature, infer the luminosity, how bright it really is, measure the brightness on Earth, and boom, I know what the distance is. So here I have another way of moving out with distances, distance scales. So another step on the cosmic distance ladder. So that is why Anytime Cannon is so important, because obviously you first need a proper classification scheme before you can actually play this game properly. But then Henrietta Swan-Leavitt, I mean, she had to look at variable stars. And she noticed that there is a class of stars known as the Cephiids, which are periodic, as shown here in this diagram. They get brighter, dimmer, very periodically, and that is simply because they pulsate. So they change size and temperature, and that changes the brightness. But the really cool thing is, she figured out that there is a relationship between the period of that pulsation and the brightness. So hey, it's difficult to measure the absolute luminosity of something, because I don't know how far away it is, right? But I can measure the period of something very easily. And now, with this relation, knowing the period, I can actually infer what the brightness, the real luminosity, the real brightness is. And from the apparent brightness on Earth, again, I can use it as a standard candle and can actually measure the distance to it. So here we had another way of measuring distances in the universe. And that proved pretty crucial, I mean, we've moved to around 1920 so far, and there is still a big outstanding question in astronomy, which is there something beyond the Milky Way? Are there other galaxies? What are these nebulae we see in the sky? No one knew for sure until Edwin Hubble actually discovered a Cepheid in the Andromeda Nebula. And so he could actually measure the distance to the Andromeda Nebula. And that was so far away that it was very clear that it was not inside the Milky Way. So there must be other galaxies. Now, of course, once you have found out that this is working nicely, you will try that with other galaxies. And so he observed quite a few galaxies, and in the end, he had, let me check my notes here. I think, yeah, he managed to find 46 galaxies. And so you could actually measure the distance to the galaxies. And you could also measure the redshift of the galaxies. And came up with the famous Hubble law, right? The further a galaxy is away, the faster it is moving away from us. Now, hey, here is another way of measuring distances now, right? Because if there is a relation between distance and redshift, if I can measure the redshift, I know the distance. Yay, hooray, another way. There is a huge, big, fat caveat, though. I mean, there is one thing we relied on, and that is that we know what our standard candle really is, and that it behaves properly. Now, that's not a given. Taking the Hubble law as an example, Hubble's original value for the constant in that law was off by more than a factor of 5. Why? Well, it turned out later that unfortunately there are two classes of Cepheids, and they have different period luminosity relationships. And now, sadly, he observed Cepheids of population 2 and then used the luminosity period relationship for population 1. And that, of course, is not particularly helpful if you want to have accurate results. So that is why the Hubble law originally was completely off the mark. So you have to be careful with your standard candles. But Cepheids offer, or at least a few ones, or at least that one offers another way of measuring a distance fairly easily and very nice, because there is a purely geometrical way of measuring the distance to that Cepheid, which has nothing to do with stellar physics or anything. Because this Cepheid here is actually surrounded by, as you can see, by this gas cloud or dust. And that reflects light. So if you have, say, a dust blob somewhere here, and you get light there, some of it will be reflected towards Earth. And now, as we know, a Cepheid is getting dimmer and brighter periodically. So really, what that looks like is illustrated in this little video. So if your Cepheid sends out the bright part, then it will move towards your dust blob there, and then it will be reflected. So the reflected light obviously will arrive at Earth slightly later with a certain delay, because it first has to get to that dust blob. So now basically, the only thing you need to know is how fast is light. We know that. And so basically, we can just measure the distance between this blob here and the Cepheid here, just by taking the delay in time, divided by the speed of light, and there you go. Boom. Done. And I think it has been used with supernova 1987A as well. So light echoes are one way of measuring distances in a very geometrical way. That's, of course, really nice because there is not particularly much that can go on there, or at least less than what might go on with stellar physics and you name what. And here is actually a video of a real observation. So let me show that as well, where you can actually see nicely these signals moving out from the Cepheid. Now, Cepheids go only that far, so you need yet another distance indicator for really getting to cosmological distances. And what you really need is something very bright because you want to look very far away. And one of the brightest things you can get in the universe is, of course, supernovae. As you might know, there are different types of supernovae. Broadly speaking, you can have a star exploding at the end of its life. But there is another type of supernova where you basically have a system made of a very compact object, a white dwarf, which is surrounded by another star. And that other star is losing mass to the white dwarf. So the white dwarf is happily accreting and gets fatter and fatter. But now there is only a certain mass limit a white dwarf can have. Because if it gets heavier than about 1.4 solar masses, it can't sustain the pressure anymore. Too much gravity then. And then you will actually get a supernova 1A. That's pretty cool because basically it will always happen at the same time. Basically, more or less when you have this 1.4 solar mass limit reached. So you would assume that basically a supernova 1A always looks more or less the same. And that, of course, is very helpful because, again, you have a standard candle. Because if every supernova 1A behaves in the same way, has the same brightness, you can, again, use that to measure distances. And that is, oops, that is missing a slide here, but never mind. That is, of course, one way which was used to really go out to cosmological distances. People were actually measuring the distance, the redshift of many supernovae, and had, as the foray had a real surprise. Because everyone was assuming that there are three different possible cosmological models. Either the universe expands, slows down, and collapses again, or it just expands ever more, or it expands ever more, but not just. But at any rate, it will always get slower. And of course, the universe has a certain habit of surprising astronomers. And the supernova observations showed that actually the universe is accelerating. It's getting faster and faster. And that, of course, led to this whole idea of dark energy. And of course, other observations contribute to precision cosmology. For example, you can have a look at how a galaxy is actually distributed in the universe and can see that they are sometimes clumped, but you have empty voids in between, and then you can actually simulate that and ask how much dark matter do I need, how much dark energy do I need to explain that. Or, of course, you can look at the cosmic microwave background and again do all sorts of complicated physics to infer how much dark energy and how much dark matter you have in the universe. And you basically come up with your standard cosmological model, which basically says that our universe seems to be pretty flat. And that leads to a question, if it's flat, might that mean that it is infinite? Does it actually have an end? Do we know? Is it maybe a torus or not? We don't know. The short answer is, and we can't really go there. So at the moment, we can basically just say that, look, if our cosmological model is correct, then it might be infinite. Now, of course, it might not. It might be a torus, or maybe our cosmological model is incorrect. maybe tomorrow someone comes around and actually does find a better theory of gravitation than general relativity. We don't know. I sometimes feel that dark energy, to an extent, reminds me of these things which have been swept under the rug when it came to the geocentric model. Doesn't really fit in with observations, don't really fit in with our model. Well, okay, we don't really want to let go of our head theory. Of course, there are good reasons not to, but in a way, there is this uncertainty, if you ask me. And that is, of course, why it's so important to keep observing dark energy or the effects and hopefully find an explanation one way or other. So the universe might or might not be infinite, but what actually does infinity mean? And I want to finish off by a little detour and asking, what did mathematicians make of infinity in the last 100 plus years? Before then, infinity was really something you avoided. Yeah, maybe something for theology. Yep, God is infinite, fine. Let's not deal with it on Earth. But then, shortly before 1900, mathematicians actually did start looking into infinity and not just view infinity as something you're approaching, but really asking, okay, if I have an infinite set, what does it mean? How can I actually describe it? What can I do with it? And the main name in that context is Georg Cantor. And he had some quite astounding insights. And so how do you actually classify infinity? Well, one question to ask with sets is, do we have the same number of items in it? Right? If I have 3 apples here and 3 pears here, I can compare that I have 3 here and 3 there. That's easy. But now, how do I compare infinite sets? So if I have an infinite set of apples here and an infinite set of pears here, is it the same amount? What do I do? And now what you can do is you can say that, yeah, look, okay, I basically assume that if I have a one-to-one relationship between the two sets, so I can say, this apple here corresponds to that pear here, and that apple here to that pear here, and vice versa. So like here, one-to-one relationship, or a bijection if you ask mathematicians. Then I could say that, okay, these, in a way, these two sets are, I'm not saying equal in size. That would, mathematicians would say, have the same cardinality. But in a way, they are comparable. Okay. And now we can start trying to apply that and start asking questions like, what sets are actually, in that sense, equal? And have some real surprises. And there is that nice metaphor, almost, from the mathematician David Hilbert, who came up with a hotel, Hilbert's Grand Hotel. Now, Hilbert's Grand Hotel is actually infinite. So it has an infinite number of rooms. Room 1, 2, 3, 4, 5, and so on, ad infinitum. And let's assume that Hilbert's hotel is fully booked out. Okay, and now as these things happen, there is a busload of tourists arriving. Actually, an infinite busload of tourists. So what do you do as a receptionist? Do you tell the tourists, sorry, we are booked out? Look somewhere else? Of course not. You just do the following. You ask the gentleman in room 1 to please move to room 2. So room 1 is now empty, right? You move the guy in room 2 to move to room 4. So now you have room 3 empty as well. And you do that for all rooms, right? Everyone who was booked in already still has a room. And you can nicely fit in all the new visitors. So basically, it doesn't matter if you have an infinite number of rooms, you can always put in another infinite number of guests. It might take infinitely long, perhaps, I don't know, but it works. And with similar arguments, you can see that, for example, the natural numbers and all integers, negative and positive, have the same cardinality, because you can map them 1-to-1, basically using something like that. So in a way, they are comparable. So now you could ask, okay, what about fractions? What about all the rational numbers? And basically what you can do to show that they are comparable to the natural numbers as well is you can count them. You can count all fractions in the world. Basically, you just arrange them like here. You start off by all the fractions which have a 1 in the denominator, right? Or numerator, I don't never remember which one is which. So you basically start with a 1/1, 1/2, 1/3, and then in the next row you have 2/1, 2/2, and so on. And clearly that covers all the fractions. And now, if you look at these arrows, if you look at these arrows, there is a clear path through all these numbers. So I can count them. I can give a recipe of this is the first number, this is the second number, this is the third number. So really equivalent to natural numbers. I can count them. Rational numbers are countable. But what about the irrational numbers? Now, irrational numbers have a slightly bad reputation historically. There is actually the legend that the guy who was a Pythagorean in ancient Greece who discovered irrational numbers was actually punished with death because it didn't go down well. People disagree on whether he was punished by his fellow Pythagoreans or whether the gods punished him. So was he thrown overboard or was it an accident? And it's probably just a make-up story anyway. But it shows a bit of that. People were a bit reluctant about these irrational numbers, like the square root of 2, which you can't represent as a fraction. So what about them? Are they countable? How do we know? Well, that is where Cantor came in. So he argued, let's assume for the moment that you can count the irrational numbers. I mean, every irrational number can be written as a decimal number like 0.185743 and so on and so on. So, and now again, let's assume that they are countable. That means that I can basically write them all underneath each other, like here. And yeah, I can count 1, 2, 3, 4, 5, and great. Let's assume that you've done that. So you have arranged them in this order. And now you come up with a new number, which is easy to construct. Basically, you start in the first row, and then if it's a 5, then for your new number, you use a 0. And if it's not a 5 in that first row, then you use the 5. So for example, first row is a 1, that's not a 5. So the first digit becomes a 5. And then I go to the second row, and I look at the second digit, which here is a 6. It's not a 5. So for my new number, I add a 5 in the second place. And then I go to the third row, or this time, the third digit is a 5, right? So this time I use a 0 for the third place. And then I go on like that. And then I get a new number, which clearly is an irrational number as well, because it's a decimal fractional number here. But is it actually in that list? The answer is no, because the first digit, well, is different from the first digit in the first row. The second digit is different from the second digit in the second row. The third digit is different from the third digit in the third row, and so on and so on. So this number here at the bottom can't be in that list. What does it mean? I obviously didn't count all the numbers. So the irrational numbers are uncountable. You can't count them off. And our Cantor, of course, went on, and he realized that there are all sorts of different orders of infinity, so to speak. So you've got the natural numbers, that's one. Then you've got the irrational numbers, the real numbers. and then there are even worse infinities. And then one question which came up was, is there a class of infinity between the natural numbers and the real numbers? No one knew. And he tried very hard to find out whether or not. Enters a logician named Kurt Gödel, who came up with one of the most amazing insights in mathematics, if you ask me. Because he found out that if you take any system of axioms, of statements you hold to be true, then it's always possible that in this system of axioms, if it's sufficiently powerful to describe natural numbers, it's always possible to find a sentence in that system which you can't prove or disprove. It's really like the sentence here, this sentence cannot be proven, right? So if you can prove that sentence, obviously it's incorrect, because it said that you can't prove it. So, and if you can't prove it, you can't prove it, right? So any system of axioms which is sufficiently powerful and which does not have contradictions will have such statements. And it turns out that this question of, is there something between the natural number infinity and the real number infinity? If you take the standard axioms of mathematics for set theory, you can't answer. It has been shown that you can't prove or disprove that there is nothing in between. So you would have to add some other axiom. And then, of course, you could make up your mind, but then you still would get other things you can't prove or disprove. Which I find amazing. You would have thought that mathematics is able to prove or disprove everything, but no. I leave it to you to make sense of that. I think the best way to deal with it, I think, is to remember that at the end of the day, we are on Earth, we are in Cape Town, we are at the South African Astronomical Observatory, and over there, at least if you are at the SLO in person, there are some maps and some water, some tea, and some cookies. So I think it's a good idea to, instead of thinking too much about the size of the universe and the infinity of numbers, to just have a cookie instead. Thank you very much. And of course, I'm happy to answer any questions.
Yes, I have a statement. I don't know. Can you hear me?
Yes, loud and clear.
I have a statement, which is a true statement, which is that in April, I bought a book about infinity, but it's taking me forever to read it.
Yeah.
Christian. Yes.
What was the orbit of Gaia?
To be honest, I would have to check.
Did it go around the sun?
No. I think it was basically going around the Earth. I think the baseline is basically 300 million kilometers for Gaia, but I would have to double check.
Now the James Webb Space Telescope, that's at L2, is it? Or is it L1?
I think
L1. Okay. Now what kind of orbit is that? How much? Is that a longer baseline?
that is terrifically long away from Earth. Yeah, it's 1 million kilometers or more, isn't it?
You know, could that be used? That goes around the sun, doesn't it? The same distance from the Earth all the time.
Yeah, move with the Earth. Yeah.
Now, could you use that to work out the parallax of very, very faintly distant stars?
I doubt that, because you probably don't have the instruments of measuring the parallax sufficiently accurately. I mean,
She bought that L2. Maya and JWST are both there.
Oh, that is true as well. Yeah.
Yeah,
Oh, so.
both.
Oh, okay.
But one of the key things on Gaia is basically a very, very accurate clock, right? That's something James Webb would not have. For example, so it's different use cases at the end of the day.
You come back to infinity again.
Yes.
Doesn't it depend on your definition of it? If infinity is just the universe and you say there's multi-universes, or if infinity is the whole, everything there is, then it will not have to be infinite. So there's always something else. If you say if it's the finite side, there's always something outside.
But if there are other universes, right, which we don't know,
Yeah, well, even if ours is the only one, surely it must be infinite. But if it's finite, there must be an edge to it. If there's an edge, then there's something beyond the edge.
well, not necessarily, right? I mean, you could argue that if space and time in our universe is all there is, then there is nothing outside it, because there is no outside.
Yeah, but wouldn't that imply that it is infinite? Because you could always travel further.
No, not necessarily. I mean, say if you take a two-dimensional sphere
Mhm.
and just imagine that there is no such thing as that third dimension in which it lives, right? Then it's finite, but it has no
Yeah.
outside, so to speak.
Then you come across the problem as to what is it in?
Yeah, that's the thing. There is nothing. There is nothing, right?
The problem is our brains are not evolved enough to imagine that.
Amen to that, yes.
We can't imagine four spatial dimensions, can we?
No.
But we can prove them mathematically.
Yep. We have mathematical tools, but we can't imagine it. Yep.
I guess it's the same as if you can imagine 3 bottles on a shelf. You could probably imagine 4 bottles on a shelf. But can you imagine the difference between 99 and 100 bottles on a shelf 20 meters away from you? You can't really imagine that, but you know what it means. You can calculate it, but
Yes.
you can't imagine it.
Yes. I guess ultimately our brain is limited, yes.
But as Stephen Hawking once said, for a fuller understanding of the universe, we need to first medically enhance the human brain.
I'm not entirely sure I want to try that, but
Yes. We're going to have a few guinea pigs that volunteer.
yeah, not me.